I'll be taking you on physics for today. So we'll be treating waves. So we'll just be treating some key ideas that are very, very necessary under waves. Alright, so we are treating waves. Right. So what do you understand by a wave? We said a wave is a disturbance which travels outward from a source, carrying energy along with it. That's the most simplest definition for a wave. We said a wave is a disturbance. A wave is a disturbance that travels outwards from its source, carrying energy along with it. Said a wave is a disturbance that travels outward from a source, carrying energy along with it. So that's the simplest definition for your waves. We said a wave is a disturbance that travels outward from a source, carrying energy along with it. Now we're going to classify our waves into two types, or let's say we're going to classify our waves into two. So how do we classify our waves? Classification of wave. So we say one, we have mechanical waves, and two, we have electromagnetic waves. Electromagnetic waves. So what are mechanical waves? From the name mechanical, or let's just put it, what are mechanical waves? These are waves that require what? Material medium for their what? Propagation. So they require what? Material medium for their what? Propagation. Examples, you can say water wave. You can also say what? Water wave. You can also say sound wave, etc. They require something for them to be transmitted altogether. So for your water wave, then your sound wave, they require material medium for their propagation. So let's move to the next one. We have electromagnetic waves. So what are electromagnetic waves? These are waves that do not require material medium. For their propagation. So what are the examples of these waves? Examples, we have this acronym RIVUSG. This is your radio wave, infrared ray, visible light or sunlight, ultraviolet ray, X-ray, and gamma ray. Your radio waves, your infrared ray from heat or fire, your visible light or sunlight, your ultraviolet ray. I think everybody's common with X-ray using the hospitals. Then we have our gamma rays. So these waves here, they said they do not require material medium for their propagation. Another thing that you need to note here is that they travel. These waves, this kind of waves, travel at the speed of light. And what's the speed of light? You know that our speed of light v is equals to 3 times 10 raised to the power 8 meter per seconds. Are we following? So this is that on electromagnetic waves. All right. Now we're going to go to types of progressive wave. So what are the types of progressive wave? All right. So we have transverse wave, and we have longitudinal wave. Alright, so your transverse wave, what are transverse waves? These are waves whereby we have the vibration of the particle is perpendicular to the direction of what? Of the motion. So I'm trying to say they are perpendicular. Then your longitudinal, these are waves whereby you have the direction of the vibration of the particle. How would you get that? The vibration of the particle is what? Is along or in the same direction as what? As the direction of motion. So what I'm trying to say is this is the particle itself, and this is the direction of motion. Here you have the particle, and here you have the direction of what? Motion. So let me come again. What are transverse waves? These are transverse waves are waves whereby the particle itself, the vibration of the particle itself, are we together, is what? Is perpendicular to the direction of what? Motion. A very good example I use for people is this. Transverse wave is a, let me restate it now. Transverse wave is whereby we have the vibration of the particles are perpendicular to the direction of what? Motion. So examples of transverse wave are water wave, altogether, and also your electromagnetic waves too, altogether. Now, what do I mean by transverse wave? Now, this is transverse wave. For example, we say water wave. If you have an object in water now, say this is water. This is the object here now. Altogether. Now, or your sea now. So this is the water, right? This is the particle. Now, the particle will be moving what? Up and down. Are we together? But let's assume that this object is drifting along this direction. This is the direction of motion. But the particle itself is vibrating. Vibrating is a form of movement, yes or no? So it's vibrating what? Up and what? Down. Then if you notice it's forming an angle, now it's 90 degrees. That's why we say they are perpendicular. The vibration of that particles itself is actually moving what? Up and down. But the direction of motion is here. You must have seen, okay, you must have watched films whereby someone is in a boat and could not pedal. Maybe after 3 days, you shall know that the boat will move along one direction, can find itself in another place. What actually happened is the direction of motion is like this. But it's quite possible that, okay, the boat was going up and down, maybe in a stormy sea, up and down, up and down, up and down. But it was moving along what's a direction. So that's why we say they are transverse wave. The direction of the vibration of the particle itself is perpendicular to the direction of what? Motion. Altogether. That's our what? Transverse wave. Then what of longitudinal wave? A very good example of a longitudinal wave is your sound wave. Like I said our sound wave, this is for transverse. Like I said, our sound waves, the vibration of the particle is what? Is parallel or is along the direction of what? Motion. A very good example I use for people is this. If you have your loudspeaker here, say this is me, and say that this is you. You must have watched Tom and Jerry now. Now, this is your speaker, quite alright. Now, if you direct this speaker to me, that is the direction of motion. Now, between me and you, who will feel the effect if this speaker is directed towards me? If this speaker is directed towards me, are we together? Between me and you, who will feel the effect? It's me now, obviously. It's just like if you stand in front of a speaker. It's as if your ear wants to go deaf. That means because the speaker is directed towards me, I'm feeling the impact. Yes or no? And what impact am I feeling? I'm feeling the wave particle what? Impact. Are we together? I must avoid Tom and Jerry now. And so the direction of motion is along where am I facing this loudspeaker. Are we together? Then you now at the back, you will feel less effect of the sound. Yes or no? So the direction of motion is this way, because the direction of motion is actually where you direct this loudspeaker to. Then the wave particles is the what? The vibration of the what? Particle itself. Are we together? So that's why we say, okay, for longitudinal motion, this is whereby the vibration of the particles are along the direction of what? Motion. So this is transverse and this is what longitudinal what wave. Are we together? All right. Now moving on from here. All right. The next thing I want to do is we want to represent our wave. Traveling in the positive x direction. So you're gonna have a graph like this. Then you have something like this. This is the most simplest representation of your wave. Both your transverse and longitudinal waves are represented like this. Are we together? And this is a sine wave. It starts from the origin. This is a what? Sine wave. Are we together? So it's sinusoidal wave. Are we together? Now we have to note some things here. Now let's assume this is y, which is the displacement, and this is what? X. So there are some things we need to note here. Here we call this point that you see that is at the top, we call them crest. Now all these points which are the bottom, we call them what? Trough. I was following. Now your amplitude, we have what is referred to as amplitude. Now the amplitude is this point here. And what's amplitude? We say our amplitude is the maximum displacement. In a wave. The maximum displacement in a wave. So this is your what? Amplitude. Are we together? Alright. What else again? We also know that under this representation of our wave, we know that a wavelength is the distance. Between two successive crests or trough. So what am I trying to say? That's from one crest to another crest, I'm going to be having what? One wavelength. Also from the trough to another trough, I'm going to be having what? One wavelength. So we say a wavelength is the distance between two successive crests or what? Or troughs. Are we following? Alright. Okay. Now, mathematically, how can we state this? Since we say this is a sine wave, we all agree this is a sine wave, yes? Now, mathematically, for a wave traveling in the positive x direction, are we following? Mathematically, for a wave traveling in positive x direction, we say that y is equals to a sine, where a is what? Amplitude. A sine 2 pi ft minus 2 pi x over what? Lambda. This is our general equation, which we will tag equation 1. Are we following? We know that a is amplitude, y is displacement, f is frequency, t is time, and lambda is what? Wavelength. So let's define some terms. Here, lambda is wavelength, f is frequency, we've defined y as displacement. What else again? We've defined our t as time. Alright, so these are the key terms. Now we brought out equation 1. Now recall v is equals to what? Lambda f, which is an equation for wave, right? So v is equals to what? Lambda f. This is an equation for wave. Now what do we do now? We know that, let's make f the Pareto formula. So f is going to be what? V over what? Lambda from here. Now we're going to substitute this guy into equation 1. So that will be y is equals to a sine 2 pi multiplied by v over lambda, t minus 2 pi x over what? Lambda. Now if you notice, some things are common here, so I can bring it out and see, y is equals to a sine 2 pi over lambda vt minus what? X. That's equation 2. Are you following? So these are like several ways you can represent your wave. They are not necessarily the major equation is this equation 1. From equation 1, you can use equation 1 and this to derive any other thing altogether. Alright. Another thing again that you see representation of is, okay, they are going to say, you recall that your f frequency is 1 over period, right? So we're going to rewrite equation 1 again. That's y is equals to a sine, we have a sine 2 pi ft, so this will be 2 pi, what's f? 1 over t multiplied by t minus 2 pi x over what? Lambda. Rewriting as, or better way, y is equals to a sine 2 pi t over t minus 2 pi x over what? Lambda. So it's still the same thing. You can see the major equation still remains equation 1. The major equation still remains equation 1. So that is our equation 3. This is our equation 2. This is our equation 1. Alright, so the major equation still remains equation 1. Now I'm going to do something to equation 1. I want to rewrite equation 1 again. I want to rewrite equation 1 as something else. Now recall that we said y is equals to a sine, the general equation 1 is a sine 2 pi ft minus 2 pi x over lambda. Now we're going to bring out some new terms now. W as angular frequency, which is denoted as 2 pi f. And what else again? We're going to call k, which is called angular wave number or sometimes wave number. Angular wave number or simply wave number, which is equal to 2 pi over what? Lambda. What else again? Then we are going to say that, okay, this kx, which is 2 pi x over lambda, are we together, is equals to our phase difference. Phase difference. Are we together? So, okay. So let's go. So what would that be? That means if I represent this equation 1 with all these terms, I'm going to have y is equals to a sine 2 pi f is w, right? 2 pi f is w. So either will be a sine wt, 2 pi over lambda will be k, which is angular wave number, kx. So where k is usually, the unit of k is usually rad per meter. So is that meter or centimeter? But I'm just putting meter as or rad per distance. Let me put it as distance. Rad per the distance. This is angular wave number altogether. Alright, so you see, we're going to treat questions under this, but for now, I'm just giving a note or a general overview of the whole topic. So like I said, the major formula is still equation 1 altogether. And I'm going to call this guy equation 4. So we are okay with this now. Altogether, I hope there is no issue. Now, from here, we move further. Now, we said sound waves require material medium for their propagation, right? We said sound waves require material medium for their propagation. Alright, so okay, I'm trying to see what's next here. We've defined this already. Okay, say sound waves are longitudinal waves altogether. Alright. Okay, our transverse wave, we said they require material medium for the propagation. So we have water wave, electromagnetic waves, and sound waves. Electromagnetic waves. Alright, I'm coming. So I'm going back to mechanical waves. This is what I'm trying to bring. These are waves that require material medium for their propagation. That means sound waves require material medium, yes or no? So there are different ways you can transmit your sound: in water, in air, in steel, but sound waves cannot travel through vacuum. We know that our sound waves cannot travel through vacuum. Now there's something about this your sound wave. The velocity is dependent on your temperature altogether. So for sound waves, we know that our velocity is directly proportional to what? Square root of what? T. Meaning that as v increases, as your velocity increases, t also what? Increases. Where v is velocity of the wave and t is what? Temperature. Alright. So if you introduce your constant here, v is equals to k root t, and k is equals to v over root t, which can now be said as v1 over root t1 is equals to v2 over what? Root 2t. Then t is temperature in Kelvin. You can take note of that altogether. Alright, now before I go on, I'm going to just do a summary now, quick summary. What are the properties of waves? What are the properties of waves? So I'm just going to do a summary. All these topics, all these properties, they're also a part on their own. So 1, reflection. You know reflection now, when something hits a barrier, it bounces back, alright? All those things. So we have reflection, we have refraction, we have diffraction, we have what? Interference. So reflection is whereby if your wave on encountering an obstacle, it bounces back. So that's reflection. And one use of reflection is in the use of determining is one importance or one application of reflection is echo. Another application is used in determining the depth of oceans altogether. So that's reflection. That's whereby if the wave encounters a barrier, it bounces back. So imagine you directing an instrument that sends wave down the ocean. So on getting to the ground, the wave bounces back. Then from there you can calculate the time. You can now use the time, your velocity to get your what? Distance. So under our reflection, we have the idea of, I just want to do a summary. For reflection, that if this is a barrier, this is you. Say you clap your ends altogether, waves are transmitted. On encountering a barrier, the waves what? They bounce back. You send a wave this way and the waves what? Bounce back. Let's say this covers s distance, this covers another s distance. So we know that okay, v is equals to what? 2x over what? T. Where x is distance from you, or distance between you and the barrier. So like I said, I don't want to touch the topic fully. So we have reflection, we have refraction, we have diffraction, and what? Interference. So what's refraction? Whereby you're having your wave traveling across two different media. So there you have your refractive index. Now under your refraction, the wavelength will change, the velocity will change altogether, and the speed, the wavelength, the velocity will change, and the direction will change, but your frequency remains constant. So here we are saying that here for our refraction, frequency remains constant. Frequency remains constant. So when do you have refraction? Whereby your wave is traveling across two different media, say water to air, air to water, water to glass. That is two different media. So you are going to be having refraction. Then diffraction. This is whereby a wave on encountering an obstacle has the same size as the wave. It tries to what? It pass around the obstacle. See, if you have your wave like this, if you have an obstacle like this, and you have a wave, on reaching this obstacle, are we together? Now, if this wave is the same dimension as this obstacle, it will just spread out. So that's what diffraction. Are we together? Then interference. This is where you have two waves that are what? Superimposed on what? Each or there. All right. So like I said, all these topics will still be treated on its own. So the next thing we want to look at is we want to look at what we refer to as standing waves. Now, before I go further, what distinguishes your transverse wave from your longitudinal wave? It is what we refer to as polarization. And what's polarization? We have a guy called polarization. Polarization differentiates your transverse from longitudinal. Transverse from longitudinal. Only transverse wave can be polarized. Only transverse waves can be polarized. Now let me cancel this for now. Can be polarized. For example, we said examples of transverse wave. You recall we said examples of transverse wave are, what do we have it as? Examples of transverse wave. Let's look at it. We said electromagnetic waves, and electromagnetic waves contain what? We said RIV USG, right? Now, let's consider that we are dealing with light. Now, if you have your light can be made to be vibrating in different directions, different direction, and the direction of motion is this. Now, you want all these vibrations to go in just one single place. You want it to just move probably in this direction only. So what have you done? You have applied what we refer to as what? Polarization, whereby you have made different what? You have made different waves traveling in different directions to move along what? One direction. That's what we refer to as what? Polarization. How would you get that? You have made those vibrating bodies to just move in one simple direction. That is what? Polarization. So it's only transverse waves that can be polarized. Your longitudinal waves cannot be polarized. Why? Your longitudinal waves, the direction of motion and the wave, they are moving along the same line. So what is there to polarize? Nothing. When your transverse wave, you want it to go in one direction. How would you get that? So if for your light is, you know that when you're on your light, it has multiple directions. So you can just make it to go in a single line. For example, you're on your torchlight now. You allow it to face this direction. Are we now? So that is what we are trying to do, polarization. You try and make all those vibrations to go in just one single axis or something. That is what? Polarization. Alright. Now, what we want to do next is very, 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 very tricky. What we want to do next is very, very tricky. Alright. So, the next thing on our list, we will be looking at what's referred to as standing waves. Standing waves, also called stationary waves. So, what do we know by standing waves? We said standing waves. This is when you have two waves that are traveling in opposite directions. When you have two waves that are traveling in opposite directions on top of each other. So that is what we refer to as what? Standing waves. So let me draw the diagram for a standing waves. We say you have two waves that are traveling what? In opposite direction. So this is one wave moving along this direction, as you can see. Now we're going to say this is wave 1. You also have another wave, but it's traveling in the what? In the opposite direction. Are you following? And this is what? Wave 2. And they are what? On top of what? Each other. Alright. Now, are you with me? Now, we call some things here. We refer to some things here as nodes. We refer to another thing as what? Antinodes. Nodes are denoted as N, antinodes are denoted as what? E. So what are nodes? Nodes are regions of the wave that are said to be what? Permanently at rest. While antinodes, what are antinodes? Antinodes are regions of the wave that let me put it. Antinodes are regions of the wave halfway or half points between two consecutive nodes. between two consecutive nodes, they are said to have maximum displacement. Remember we said amplitude here in our last something. We made mention of amplitude here, and we said these are regions where they have maximum displacement. So it's also the same thing for this. We are saying nodes are regions of the wave that are said to be permanently at rest, while antinodes are regions of the wave halfway between two consecutive nodes that are said to have maximum displacement. So judging by this definition I've written here, so these are my nodes. You can see it's as if the wave started. These are nodes. The wave started from here, it got to this point, it relaxed, it stopped, then you have another wave that continued. So this is nodes, these are nodes, these are nodes. Then what did you say antinodes? Did you say antinodes are regions of the wave halfway between two consecutive nodes? This is one node, this is one node. They are halfway. That means this is your antinode. And we said there are regions that have maximum displacement. And we said antinodes are halfway between two consecutive nodes. So these are antinodes, these are antinodes, and these are antinodes. Are we following? Now, let's note something here. If you have three consecutive nodes, from your three consecutive nodes is what you are going to be having as one wavelength. Remember the other time we said between two successive crests of two successive troughs is where you have one wavelength. But in between three consecutive nodes, you are going to be having one wavelength. So what am I saying? If you have from here 1, 2, 3, you are going to be having one wavelength. Are you following? Now if you look at this wave started from here, ended here, started from here, ended here. So it's as if this thing is divided into two equal parts, yes or no? That means from here to here to this point, I can call this region lambda over 2. Then from here to here will be lambda over 2. Are you seeing what I'm saying? It started here, end here. It's as if it's completing I won't say a full circle, half circle, another half circle. So that means you can divide this wavelength into two equal parts, alpha over 2, alpha over 2. Now we already said antinode is halfway between two consecutive nodes. If from this node to this node is lambda over 2, and antinode is halfway between two consecutive nodes, it means that from this region to this point here, to where I have my antinode, it will be lambda over 2 divided by 2, which is lambda over 4. Now let me come again. We said in between three consecutive nodes, from a node to a node to a node, we have one wavelength. Now this wave started from this point to this point, half circle, another half circle. It's as if this is divided into two. So this becomes lambda over 2. We already say antinode is halfway between two consecutive nodes. That means lambda over 2 divided by 2. This will be lambda over 4. This will be another lambda over 4. So these are the questions they can ask on your stationary or standing wave. So in between three consecutive nodes, you have one wavelength. From a node to a node, or antinode to antinode, node to a node, antinode to antinode, you are going to have lambda over 2. From a node to an adjacent antinode, from a node to an adjacent antinode, you are going to have it as lambda over 4. So the question can come in, okay, what is the distance between three consecutive nodes? That's one lambda, or one wavelength. From a node to a node, lambda over 2. From an antinode to an antinode, lambda over 2. From a node to an antinode, it is going to be lambda over 4. So those are the questions they do ask in JAMB. So standing or stationary waves. Now these are standing or stationary wave. Earlier we made mention of transverse wave and we made mention of longitudinal wave, right? Now under here we are going to be having stationary transverse wave, and we are going to be having stationary longitudinal waves. Stationary longitudinal waves. We have stationary transverse wave and we have stationary longitudinal waves. Alright, I'm going to end the video very soon. So we have stationary transverse wave and we have stationary longitudinal waves. So where are your stationary transverse wave? Where are they set up in? Your stationary transverse wave are set up in in your vibrating air columns. Vibrating air columns, which I mean open and closed pipe. Are you following? Then your stationary longitudinal is set up in your strings. Are you following? Now, what do I mean by open pipe and what? Closed pipe. Open pipe. We said they are vibrating air columns. Vibrating air columns basically means a pipe whereby you have an opening, you have an end. You understand? The vibrating air columns. For example, your recorder, anything that has hole that you can make sound from, your recorder, your saxophone, all those things are vibrating air columns. You can have it to be open and closed pipe. Open pipe in the sense that both ends are open. Closed pipe, one end is closed. Are we following? Then your stationary longitudinal waves are set up in your what? Strings. Please take note of that. So we said for an open pipe, open at what? Open at one end. For your closed pipe, it is closed at one end. For your open pipe, it is open at both ends. For your closed pipe, it is closed at one end. So if I want to draw a diagram, this is a diagram of an open pipe. Both sides are open, but for your closed pipe, one side is what's closed, then the other is what's opened. So that's why I say for our open pipe, it is open at both ends. For your closed pipe, it is closed at what's one end. Are we following? We remember we started with stationary or transverse wave. We've defined some key terms, nodes, antinodes. We went to stationary transverse wave. We went to what? Stationary what? Longitudinal waves. Now, our next topic, I'm going to end the video now. The next part of the course, we will explain the open and closed pipe aspects, the necessary formulas, it will explain the string aspects, and we'll be doing the diagram aspects. So, if you have any difficulty with the course, I believe I've done justice. Just go back to the video, restart, and rewatch. Alright, thank you for listening. Let's stop here, then continue the next video. Thank you.